Hi, hello everyone. I Pratham on behalf of the Dark team. Welcome you all to yet another of a Baithak. A bit about the Baithak and what we do at Dark. The Dark began in 2023 as a book review journal publishing original reviews across disciplines and genres. From the very good get-go, we have tried to reimagine the form of the book review itself, encouraging writing that moves beyond summary to engage deeply, reflectively, creatively, and critically with the world that a book opens up for us. Over time, we have grown into a biannual academic journal that now includes reviews, explainers, commentaries, and research essays. Each issue is built around a central theme, bringing together diverse voices that explore the intersections across social sciences. A double-blind peer review process ensures rigor, while editorial approach values accessibility and creative thought. Beyond the journal, the Dark has also grown into a vibrant collective. Through our reading groups, we meet every month to discuss a shared book, discovering new perspectives through conversation. Through the Dark Weekly, we publish personal essays, topical reflections, and explainers that extend our conversations into the present moment. The Dark Baithak is a humble attempt to huddle together a small gathering of scholars, writers, students from different fields to present ideas and initiate dialogue, bringing critical conversations to life. For our session today, we have Dr. Paul Heron. The session today is titled 6,000 and Counting, an overview of the research field of exoplanets. A bit about our speaker today. Dr. Paul Heron is an astrophysicist with a research background in exoplanets and astronomical data analysis. During his PhD and later postdoctoral work at the State Observatory Heidelberg, part of the Heidelberg University, his research focused on exoplanetary systems around giant stars, Dopplers, spectroscopy, and observational instrumentation. Working with the SONG consortium at RS University, he developed a modular analysis software that is now part of the official data reduction pipeline used at several telescopes worldwide. Alongside his research, he was actively involved in science outreach through popular science writing, planetarium, and night sky observation tools and events such as Astronomy on Tap. Apart from his academic work, Dr. Heaton has professional experience in data science and interdisciplinary project coordination. He currently serves as project manager for skilled workers at the Geek Institute, Max Muller Bhavan, New Delhi, supporting initiatives related to skilled migration and international across South Asia. We extend the heartfelt welcome to Dr. Heron. Whenever you're ready, over to you. Thank you.
Thank you so much. Thank you so much, Pratham, for the very kind introduction. I feel honored to be here and to be able to present in this really amazing environment. I've been part of the Dark Baithak sessions before in the audience, and yeah, it's amazing to be able to present in front of so many curious and interested people here. And I will immediately dive in. Let me just quickly try and share my presentation that I have prepared for today. You should be able to see it now. Is it visible? Perfect. Okay. So as has been announced, the title of my presentation is 6,000 and Counting. An overview of the research field of exoplanets. And we will get to the number of 6,000, but probably you can already kind of imagine what it refers to. But I'm starting off this presentation with first this picture. It's a recent picture that has been taken by the Artemis mission 2 that orbited once around the moon and came back to Earth. And I like this picture because it shows, it shows the one planet in the galaxy where we know that there's life and that we know very well ourselves, and that's the Earth. And starting from here, really, I mean, all our research on anything happens, right? But also all our research on finding out, are there similar kind of environments elsewhere? And I'm going to try and keep this presentation, kind of focusing on the phenomenological side of things, explaining the kind of concepts without going too much into technical or mathematical details. I have a few formulas here and there, though. There's no physical or astrophysical talk that's possible completely without, I would say. So starting off, it was here on Earth that, already a long time ago, probably as long as there have been humans and not just Homo sapiens, but also other species of humans, in the night skies, when one is not exactly sitting in the middle of Delhi where you have a lot of stray light, but you can actually see the night sky, you cannot help but wonder, right? Like, what is all of this out there? What are all of these small dots up there? And people already in ancient times, they looked at this and they really started kind of questioning, you know, what do we see up there? What could this be? And they try to kind of assign what they saw some meaning. And I have just, you know, put in here into this picture of the night sky some of the things that people saw in this in antiquity a long time ago. What they and how they try to kind of make sense of this, and that's obviously stellar constellations. But also already in those times, and probably also already before the old Greeks and the old Indian kingdoms here and in the Middle East, and people kind of figured out that, you know, there are differences in what they see there on the night sky. So you have the kind of, you know, the large majority of the dots you see up there are fixed stars. So they always seem to stay in the same position, no matter the kind of, you know, time of the night you look up there, or the time of the year, or over the years, it also doesn't change much. Relative to each other, these stars always stay in the same position. But you also have some other kind of dots up there on the night sky, and those are wandering stars. So as the Greek called them, if I'm pronouncing this correctly, I cannot be sure, planetes asters or planetai. And this is where we have basically our modern word for this kind of object from. So that's a planet. And the Greeks, they knew 7 of those planets. Those were the moon. So interestingly enough, they called moon a planet because it was also one of those wandering objects on the night sky. Mercury, Venus, the sun also, because all that they could see, it's a bright object on the sky and it wanders across the sky. Mars, Jupiter, and Saturn. And still in ancient times, like mostly people stuck to the kind of heliocentric model, assuming basically, you know, we have the Earth in the center of the known galaxy or universe, and then around it, there were different theories. You have kind of spheres, and like the fixed stars, they are on like an outer sphere, and then these wandering planets, they are kind of like in inner spheres where they kind of move around. And this was kind of the dominating theory all throughout antiquity. Interestingly here, for example, in India, a guy called Aryabhata, he came up, or he kind of understood, okay, there must be something going on here, and that's Earth's rotation. So instead of basically saying, yeah, the sun orbits around the Earth with a one-day period, he already figured out, okay, no, it's probably the other way around. The Earth is rotating around itself. So this I found interesting, because this was kind of already a first step into a more modern understanding. And then obviously came the big revolution in the late Middle Ages, when the new model, the new understanding was accepted, that instead of everything going around the Earth, it's actually planets that orbit around the sun. And this is how we can explain these movements across the night sky. Also, I've put here already, I think, an interesting quote, because looking at all of these objects up there, people also, or some people started wondering already back then, like what might be going on these objects out there. And I have here a quote by Democritus. There are countless worlds of different sizes, and some of them neither the sun nor the moon are present. In others, they are larger than ours. Still others have more than one of them. Some worlds have no animal or vegetable life, nor any water at all. So you can clearly see that already back then, people also kind of wondered about, you know, is Earth all there is, and all that there is for life? Or are there maybe other parts of the universe where this might be present. A big change came then when telescopes were invented, roughly 500 years ago or 400 years ago. So telescopes, and I've got here an overview of two different kinds of telescopes. So we have like refractors and we have reflectors. The difference being that in one kind of telescope you use lenses, optical lenses. In the other one you use mirrors. But both work in principle in the same way, basically by using a larger aperture, so a large lens or a large mirror, you are able to collect much more light than it is possible just through the tiny pupil of our eyes. And this helps us to see much more faint objects. So stars can appear in the sky that you might never have been able to see before. And also, if you get the properties right of these mirrors and lenses, you can magnify what you see on the sky. So it helps you to really kind of look at it closer and discover more. And this really then kicked off a new era in astronomy also, where in quick succession, starting from 1781, additional planets in the solar system were found that, in ancient times were not known simply because they cannot be seen by bare eye. So we had Uranus discovered. Shortly after, then came Neptune. Interestingly, Neptune was already predicted based on kind of like the orbit of Uranus, which seemed to sometimes be perturbed a little bit. And so basically, this is an early kind of example of how theory of gravitation can help us also to then to predict something that we are not able to see yet, right? So basically, by Uranus's gravitation disrupting Neptune's, other way around, by Neptune's gravitation disrupting Uranus's orbit, it could be predicted that there must be another planet there, and also roughly where it should be. And then they were able to actually find it also. Similarly, it went for Pluto, which was discovered in 1930. And then in 2005, in between, many other small objects were discovered, asteroids and so on. Then in 2005, Eris was discovered. And this was really a problem because Eris is, it's very small, yeah, but it's kind of bigger than Pluto. And with the discovery of Eris, it became clear also we will probably find many more objects like Eris and like Pluto in the solar system. And so basically, astronomers had two ways they could go. Either they would assign all of those the official category of a planet, or they would have to redefine what is a planet in order not to, having to name and basically remember at the end something like 1,000 different planets. So the International Astronomical Union in 2006 came up with a definition. So a planet is a celestial body that A, is in orbit around the sun. So it shouldn't orbit something else. For example, the moon orbits the Earth. So it's not a planet, but it's a moon. But the Earth orbits the sun, so it's a planet. It should have sufficient mass so that it can assume a nearly round shape. So an asteroid, for example, is so small that its own gravitation is not strong enough to bring it into a round shape. But for Earth, for example, this is the case. For Pluto and for Eris, interestingly, this is also the case. But definition or requirement C, this object should have cleared the neighborhood around its orbit, meaning that basically through its gravitational pull, it should have either attracted all other objects that are close by or should have ejected them from its orbit, so that it's really the only big object that is orbiting there. And this, for example, is not the case for Pluto and Eris, which orbit around the sun in a region where there are many, many other similar objects. So since then, it was a big controversy back then that Pluto is not a planet anymore. Now we have 8 planets in the solar system. Everything else is basically classified either as dwarf planets, satellites, so that's moons, or small solar system bodies. And this is then what we basically have today as the kind of as the kind of big objects in the solar system. So the 8 planets, their names are here on top of the planet. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Then we see here those smaller dwarf planets, Ceres, Pluto, and Charon, where, you know, Charon, sometimes it's said it's a moon of Pluto, but really both are so similar in size that both are kind of, I would say, dwarf planets that just, you know, revolve around each other. And then there's Eris at the very outer edge. And what we can already see here, and mind you, so the distances between the planets and to the sun, those are not to scale. Yeah, so this is just a representation here. But the sizes of the relative sizes of the planets and also the relative size to the sun, this is to scale in this picture. So what we can clearly see here is kind of very different, again, types of planets. Yeah, so we see the 4 innermost planets, Mercury, Venus, Earth, and Mars. Those are fairly small, and we also know for all of them that they have a very hard surface. Largely, their mass is basically made up by rock, by metals, you know, solid material. And then some of them, so Venus, Earth, they have, and also Mars to some degree, have like an atmosphere. So those are called terrestrial or rocky planets. Then we have the big, huge gas giants. They are much more massive than these small terrestrial planets, Jupiter and Saturn. And they mainly consist of gases. It's kind of speculated. We are not quite sure what's in the innermost parts of Jupiter and Saturn. It's assumed that there is some kind of a solid core in both of them, but that solid core is probably, you know, comparable to size, maybe in Earth, maybe even smaller, maybe a little bigger. But largely the mass of these planets is made up completely by their dense and extremely large atmospheres. So those are called gas giants. And then we have at the outer part of the solar system, Uranus and Neptune, who kind of fall in between. Their masses also, to a large degree, consist probably of their kind of the gas envelopes that they have. But they are also assumed to have kind of like probably an icy core, icy because they are so far away from the sun. It's very cold there, so probably, you know, anything freezes quickly there. So those are called kind of Neptunians. I have no idea why they chose Neptune to kind of name it and not Uranus, but maybe Uranus just doesn't sound so well. So Neptunians here the name became. So this is kind of, you know, the solar system as we know it today. And while there's, as I said, a lot that we don't know yet, like, for example, the course of these planets, of the gas giants, we know it fairly well. And in this part of the solar system where these planets orbit, there are not large surprises anymore when it comes to new bodies. I mean, new bodies are discovered on a daily basis, but those are then asteroids, you know, so very small objects only. But with that, so basically our system of our picture of the solar system is complete. And that was kind of already the case towards more or less mid last century. So people started again wondering more like, is the solar system special? We have 8 planets here. Is that the norm, or is it for other stars out there, for these fixed stars that are very far away? Can we expect to find planets, or are planets maybe kind of very rare in the galaxy? And interestingly, this was completely unknown, really, till roughly 35 years ago. People had no idea really what is out there. This didn't keep people from speculating and from doing great fantasy fiction on it. And in most of the science fiction where interstellar travel is kind of a theme, planets are very common. Right, so like in Star Wars, they travel from one planet to the other. You have a great variety also of different planets there. I've also put here a picture of the book, The Mote in God's Eye, which I find a very interesting science fiction, which is kind of like about a first contact between humanity and another alien civilization. But researchers really didn't know. And there were many scientists, many astronomers who were very skeptical that we would find many planets out there. So why hadn't we found any other planets? This I want to kind of just briefly explain here. So why is it hard? Most stars that we see on the night sky, they're extremely far away. I think this comes to no surprise for anyone here. I've put a short or small kind of picture here on the right side where one can see the typical distances in space. So and this is kind of measured by how long the light takes to reach there. So to Moon, it takes 1.3 seconds to reach. The light from the sun to get to Earth, it takes 8.3 minutes. So interestingly, if the sun would turn off now, we would only get to know in roughly 8.5 minutes. The next star system is the Alpha Centauri system, and that's 4.4 light years away. So one can already see here, basically by doing simple math, that it's just, insanely much further away than the sun. Right. I've also put a small box above the picture where the distance of a light year is explained. So 1 light year is 63,300 AU. 1 AU is the distance between the sun and Earth. So you can do the math yourself. 4.4 times 63,300 AU. That would be kind of like how much further the Alpha Centauri system is away from us than the sun is away from us. And now brightness that we perceive falls off with 1 over r squared, where r is the distance to an object. Yeah, so this means basically if an object is 2 times further away, it becomes 4 times fainter. If it's 4 times further away, it becomes 16 times fainter. And so this kind of, it multiplies quickly when we get further and further away. So as an example here, if the sun would be not where it is within the solar system, but if it would be where Alpha Centauri is, that other star system, that closest star system, it would be 4 times 10 to the 9 times fainter. So this is basically a 4 with 10 zeros behind it times fainter. Yeah, so it should be 4 billion then, 4 billion times fainter. So already this shows that, even to see a star far away, it's much harder. And this is obviously why we see stars only in the night sky when the sun is not there. So the sunlight doesn't block out the starlight of these faint stars. Now planets are even fainter than stars because in the visible spectrum, so where our eyes can kind of see light, planets don't emit a lot of light themselves, right? But mostly they just reflect the light that comes from the star. So the moon, for example, or Jupiter, they are so bright in the night sky because they reflect the light that comes from the sun. So this means if we would now, to start off, Jupiter, for example, is 4 times 10 to the 11 times fainter than sun. So a 4 with 11 zeros times fainter than the sun. And if we would now put Jupiter in the position of Alpha Centauri, the next star system, it would be as bright as a 100 watts light bulb at a distance of 200,000 kilometers, which is kind of a little more than half the distance to the moon. Yeah, so imagine a 100 watt light bulb somewhere in the middle between moon and Earth, and now we have to kind of find it. So this is why it's very, very difficult to find exoplanets, because these planets are just really faint. And this is the reason why we mostly rely on indirect detection methods. So we cannot directly find the planet. We have to look, in most cases, we have to look at the star that this planet is orbiting, and then kind of deduct from what the star is doing whether there is a planet around it. And I'm going to go now through a few of these techniques. And thankfully, NASA has made some very nice videos which help in understanding this. So the first technique that we're looking at is called the radial velocity method, or Doppler spectroscopy. So if a planet orbits a star, they really orbit both around their common center of mass. So basically, the planet's mass also gravitationally pulls on the star. And this means, as we can see here, that the star also kind of moves back and forth on a kind of circular or ellipsoidal orbit. And I'm just going to play it once more so I can keep on explaining what happens then. If we now look at the starlight, the starlight will periodically then be shifted more towards blue wavelengths. So it will appear more blue and more red wavelengths. So if it moves away from us, the wavelengths are kind of stretched apart. And if it moves towards us, they are kind of skewed together. This is due to an effect called the Doppler effect. And the Doppler effect, all of us know from when an ambulance drives past us. If an ambulance drives towards us at a high speed, its pitch appears to us very high. And if it then goes past us and moves away, its pitch kind of becomes much lower, right? So this is also the Doppler effect on sound waves, but similarly, the Doppler effect also exists for electromagnetic waves or for light. And this is something then we can measure. No, next slide. Yes. So how do we measure this? So we take a spectrum of the starlight, and I'm just going to say we do this with instruments like in the picture here on the right. This is a so-called spectrograph. This is actually the spectrograph or a kind of simulation of the spectrograph I built during my PhD. So a spectrograph basically takes light and then kind of disperses it into its individual wavelengths. Yeah, so that we get a nice spectrum. We see at redder light how much light comes in. We see at bluer light how much light comes in. So it really kind of helps us to look at light in the different wavelengths or colors. And then we analyze the stellar spectrum. So I have a stellar spectrum here on the bottom. So on the x-axis, you can see the wavelengths. It's in a weird kind of astronomer's unit called angstrom. Angstrom is, 1 angstrom or 10 angstroms is 1 nanometer. Doesn't really matter. But we see here basically the different wavelengths and then how much light we received. And what we can see is that it's not a flat line, but we see a lot of up and down. And these are so-called absorption lines. So basically the star the light that is emitted from the star, it goes through the gas layers of the star. And because there are different kinds of elements, chemical elements in these gas layers, each of these elements leaves a trace in the spectrum at a specific wavelength. And this is why we see all of these lines. Basically, they block out parts of the light of the star. Now, if we look at this, basically, this is like a perfect ruler. And if we now basically repeat this measurement, like over time, we take again and again a spectrum, and then we compare it to the spectra that we've taken before, we can basically look at these lines and see, do they move left or do they move right? Right? So this would mean if they move to the right, they move to longer wavelengths. And this would mean that the whole starlight is more pushed into the red part of the spectrum. And if they move to the left, they move to bluer wavelengths. And this means, the whole starlight is pushed more towards the blue end of the spectrum. And then we can use the Doppler formula, which I've put here. So basically, this change in wavelength, delta lambda, it just is proportional to the velocity of the object relative to us. So that's why VR, relative velocity or radial velocity. So this helps us to very easily basically deduce, is the star moving towards us or is it moving away from us? And then, as we've seen before, if there is a planet, then the gravitational pull has to lead to a periodic change of VR over time. And this way we are able to measure this. And basically then by looking at it exactly, how quickly does this happen and how strong is this effect, we can deduce properties of the system, like the period of the planet's orbit, the eccentricity, which means how elliptical is the orbit. A is the semi-major axis, so that's the distance between the star and the planet, and m is the mass of the planet. And just as a small example here to give you like some numbers, so Jupiter basically deduces a radial velocity on the sun of maximum 13 meters per second. So because Jupiter orbits the sun moves basically a little bit back and forth by 13 meters per second. The Earth's effect is much smaller because the Earth is less massive. So the Earth's effect is only 9 centimeters per second, which is, really difficult to measure. Now, using this method, this was basically the method that gave us the first detection of a planet around a sun-like star. And that was in 1995. And the star was called 51 Pegasus or Pegase B. You see here on the right-hand side a diagram which shows over time. So on x-axis we have the time, how the radial velocity changed, right? So when it goes up and then it goes down and then it goes up and then it goes down again. So a clear periodicity over time. And the black line that we see here is a fit, so like a model that tries to basically model the data that is collected. And by these measurements, it could be deduced that around this star, there's a planet with a mass of roughly half a Jupiter mass that orbits with a 4.2 day period. So it's really close in. It's really close to the star at 0.05 AU. So 5% of the distance between the sun and the Earth. And for this discovery, the Nobel Prize in Physics in 2019 was awarded to the two researchers who perfected the method to the degree that it was possible to make this discovery, and then also found the planet and released this paper. And those were Michael Mayor and Didier Queloz that I've put here into the box. Also, as a quick side note, this was not the first planet or the first exoplanet, strictly speaking. The first exoplanet around any kind of star was discovered 4 years earlier, or 3 years earlier, around a pulsar. A pulsar is a dead star, but those are not so interesting, these kinds of planets, because ultimately, if we want to at some point find, for example, extraterrestrial life, we assume that it must be on a planet that orbits a star, so where you have light, so that some kind of a biology can develop. So this is why this discovery was so important. Now this is the first detection technique, and I'm gonna go over 2 more to kind of cover maybe the most important ones at the current moment. So the next detection technique is somehow easier and gives us is important because it gave us the greatest number of planets so far discovered. So again, a small video. Again, if we have planets orbiting stars, and we are just lucky enough that this system is oriented in a way so that at a certain point in its orbit, the planet moves across the star as we look at it from Earth, then we will see that it blocks out some of its starlight. And this will mean that for that time being, and again, I'm just gonna play it one more time, while the planet is moving in front of the star will appear to us a little fainter, right? Basically, one can just say the planet leaves a little bit of a shadow, and the shadow falls more or less directly on Earth. And by then analyzing the starlight that we receive, we can again deduce what kind of a planet it might be. So we basically first measure the apparent brightness of the star to a very high precision. We repeat this over time and time again, and measure if there are any kind of changes in the brightness of the star. And these changes we denote as delta F. And if there then are changes on a periodically recurring instance, then we can basically use this formula here. And it's, it's fairly simple. Basically just saying, so the change in brightness divided by the brightness of the star is exactly the radius of the planet divided by the radius of the star, both of this squared. So, by just measuring this, and if we know the radius of the star, and this is something that can usually be figured out, then we can deduce how big is the planet that is orbiting it. And then also by basically looking at how often does this appear, this dimming, we can also find out other parameters of the system. So like the period of the planet, the semi-major axis again, and yeah, as I already said, the radius of the planet. So here on first, let me give a few examples. So for example, again, Jupiter on the sun, if basically the sun and Jupiter were somewhere far away and we would look at it, then Jupiter would lead to a transit depth, as this ratio is called, of roughly 1%. That means basically the light that we would receive would get dimmer by roughly 1%. Again, Earth, because it's much smaller, would have much less of an impact, only 0.01%, right? And this already, similar as with the technique that we looked at before, it already kind of should show you that a planet like Earth is very difficult to detect, at least now using these two methods. But something like Jupiter is much more easier. And again, then here looking on the right-hand side, this is the Kepler telescope, which was launched in 2009. So a space telescope that all that it did was basically to look at one part of the sky and look at it for years until 2018, and just look at a lot of stars in that part of the sky and see if it can pick up some of these dimmings. And then using basically that data, people tried to figure out if there were planets around these stars. And one very important discovery that was made with this telescope and this method was the TRAPPIST-1 system. I have to correct myself. This was not made with Kepler. It was made with another telescope, but with this method. The TRAPPIST-1 system, which is a planetary system orbiting around a very low mass, very cool star. It's called an M dwarf. And 7 Earth-like terrestrial planets had been discovered or have been discovered around this star. The interesting part is, all of these planets orbit very, very close to the star. So what we see here is basically all of this whole system of 7 planets would fit easily in the solar system within the orbit of Mercury, right? Which is the innermost planet in the solar system. However, as this is as I said, now this is a very, very cool star because it's not very massive. This still means that these planets are not, or most of them are not very, very hot. So there's something that is called a habitable zone. The habitable zone basically defines the area in space around a star where, temperatures are more or less, more or less comfortable enough to basically remind us of conditions on Earth, and thus maybe potentially allow Earth-like life to develop there. There are other factors that are important, obviously, the atmosphere of the star, of the planet, for example. But this is kind of like a first approach in kind of defining what planets might be suitable for life as we know it from Earth. And as we can see here, 3 of those planets, the planet E, F, and G, they probably orbit within the habitable zone around this cool M-dwarf star, which is denoted here in green. All right, so with this, we move on to the third detection technique that I will present. Now, I said in the very beginning, it's very hard to picture planets directly because they are so faint, but with modern instruments and kind of clever techniques, one can still make it possible for certain kinds of planets and stars. So what one does is basically just one tries to block out the starlight, which is usually much, much brighter than the planet's light. And then one is able to basically detect the planet that is right next to the star. I would just like to show it one more time. So if we block out the starlight here, then one can pick up the light from the planet. It's similar as, if basically, if you're trying to see something in the distance, and there's a car with its lights on shining towards you, if you then take your hand and block out the light coming from the car, you might be able to see, for example, someone looking on their phone screen and see the phone screen of someone standing next to the car, right? So this is called the direct imaging technique. So with that, one can be able to overcome these extreme brightness differences between stars and planets. The techniques that are employed usually is that instead of observing in the visual wavelength range where our eyes can pick up light, we move to the near infrared wavelengths where conditions are much more favorable. In the near infrared wavelengths, planets are usually less faint than stars. So basically the brightness difference becomes smaller between stars and planets. And then also, as I said, we use kind of techniques like coronagraphs to block out the starlight. And here on the right-hand side, you see the James Webb Space Telescope, which is a telescope that I think probably everyone has heard about. It was a big deal when it was launched 2 years ago. And this is kind of like the biggest space telescope that we have right now in space. It's the successor to Hubble. And this uses exactly these techniques to kind of detect planets via the direct imaging method. And we see one example of that here, where it basically looked at a star called HIP 65426. And it was able to pick up the light coming from an exoplanet orbiting that star. And this is shown down here in these pictures. So the position where the star would be, but it's not visible because the light is blocked out, is denoted by this symbol, the star symbol. But then to the lower left, we see the light from the planet that has been observed here. Okay, so these techniques, they have been gradually improved over the last few decades, and they helped us really then to kick off this this research field of exoplanets. And with that, I come to kind of our current understanding. And I already see I'm way over time, so I'm going to try and pick up pace a little bit here. So with these techniques, we were able to basically discover many more planets than previously known over the last few decades, as can be seen here. So the first exoplanets were discovered in the early to mid 1990s. And since then, you can see here, every year, more and more discoveries have been made. We have 2 big peaks here when from the Kepler mission, that space telescope I showed earlier, basically a large number of planet candidates were confirmed through analysis. Yeah, but also in the last few years, you can see that basically every year, several hundred of planets are newly discovered. And this is how we arrived at, yeah, a huge number of known exoplanets today. Looking at the distribution of these planets, so this is a diagram where all the planets denoted by the dots here are shown with their orbital periods on the x-axis and their masses in units of Jupiter masses on the y-axis, and color-coded by the different discovery methods. And you can see like a few, you can see a few kind of blobs where more planets have been discovered, interestingly. And this really is interesting because this comes back now to the types of planets that are there. So we have in the upper right corner here, the cold Jupiters. So higher planet masses, and then longer periods. This means further away from the stars. Those are basically like Jupiter and Saturn in the solar system. But we also have found a lot of so-called hot Jupiters. So gas giants, similar to Jupiter and Saturn in mass and size, but they orbit very close to their stars. And therefore they are, very, very hot. And this is interesting because we don't have any of those in the solar system. So we didn't really know that those would exist. We have found a large number of Neptunes. So out here we have Uranus and Neptune, where they would be in the solar system, or where they are in the solar system. And again, interestingly, like a large number of these Neptunes that we found, they orbit much closer in to the stars than is the case here in our solar system. Even though one has to say this is partially an kind of observational bias. Looking at terrestrial planets, so these symbols here denote the 4 terrestrial planets in the solar system: Mercury, Venus, Earth, and Mars. One can see we have barely found any planets similar to those. And this comes back to what I said earlier. As I showed, a planet like Earth is just very, very difficult to detect through these detection methods because it barely leaves an imprint in all of these. But most excitingly for astronomers, there's something in between Neptunes and the terrestrial planets, and a lot of them. And those are so-called super Earths, as they have been denoted, because they are a little more massive, a little bigger than Earth, but not quite as big as Neptune and Uranus yet. And these planets, no one had kind of foreseen that we would find planets like that, and especially not a large number like this. Again, we have nothing like this in the solar system, but yeah, apparently they are very common. And if we look at the total numbers here of these different types of planets, one can really see, yes, they are quite common. Actually, roughly 31% of all planets found to date are these so-called super Earths. And as you can see up here, only 4% found are the terrestrial planets as we know them from the solar system. However, as I said earlier, this is partly an observational bias because these terrestrial planets are very, very difficult to find. So basically looking at all of these discoveries and then using statistical methods, astronomers have attempted to kind of understand how many planets are there really in the Milky Way, and we are just not able to pick them up maybe. This is called the planet occurrence rate. And there are huge uncertainties on this, on the numbers, but it currently looks like probably there are overall at least as many planets as stars in the Milky Way. So roughly 100 billion. Probably there are roughly half as many super Earths as stars in the Milky Way. But coming to the terrestrial planets, probably, again, one has to say that, roughly half of all stars similar to the Sun host a somewhat habitable rocky planet. So this would mean there would probably be at least something like 300 million Earth-like planets around Sun-like stars in the Milky Way. And in the direct solar neighborhood, 30 light years around the Sun, according to these statistics, one can kind of expect 4 such planets orbiting stars there. And I think these are very, very exciting findings, because this means, looking again at the kind of, the kind of science fiction, this might actually be true, right? So these kind of fiction stories that have been made up with this large variety of planets and many, many different systems, this seems to really, really be the norm. I'm going to leave out this, I think. We can maybe come back to it in the questions, but I'm going to move on to the implications and outlook. So to basically sum up a little bit, from 0 to 6,000, so we can say now this is basically the number of exoplanets known today, and this number has been achieved in just 35 years. And this really brought in a paradigm shift. So it first of all sparked renewed focus on detection techniques and development of new detection techniques and instruments, but also these kind of surprising discoveries with respect to planet occurrences. They kind of really revolutionized our understanding of, what can we find out there. Super Earths were not known before. Now we know that they are very common. This is something no one had really anticipated before. And all of these findings also have very challenging implications on the old theories of how planets form in the first place. So the whole field of planet formation, that kind of also really had to come up with new ideas of how to explain all of these findings. So what we know today, as Democritus had kind of prophesized 2,500 years ago, planets really seem to be the norm. But that's obviously the next big question. What about life? And one attempt, just a very basic attempt of kind of understanding how common extraterrestrial life might be, I want to show here the so-called Drake equation, which is very famous, obviously, which tried, it was formulated in 1961 by Frank Drake, who was an astrobiologist. And he basically, with that, tried to kind of estimate how many intelligent, communicating alien civilizations are out there in the Milky Way. And it is comprised of these many different factors, starting from the star formation rate in the Milky Way. So how many stars form newly every year? How many planets are there per star? How many Earth-like planets basically are then there? Then how likely is it that life develops on an Earth-like planet? How likely is it that intelligent life then evolves out of life? Then how likely is it that this intelligent life actually starts communicating with kind of techniques that can cross interstellar distances? And then the length of time during which the civilization is active. And the original estimate, after kind of basically just putting in numbers here that were at that point of time in 1961, basically just guesses for most of these factors, maybe except the rate of star formation. Frank Drake arrived at an estimate between 20 and 50 billion civilizations that might be out there. What I find interesting, like using today's knowledge, this hasn't really changed much. So what we know today is, again, to a better degree, the star formation rate in the galaxy, and also to some degree how many planets are there and how many Earth-like planets are there. But all of the other factors, we have really still no idea about. So even using today's knowledge and then this equation, we can arrive at anything between basically 0 and many billion. So basically meaning there's just us, or life is everywhere. And I think this is a very even though this equation doesn't help us much there in arriving at an answer directly, I find it very inspiring, because this shows us what we still don't know. And this therefore also kind of pushes us towards where research is needed. And that is a lot of interdisciplinary research. So we need to, for example, understand how likely it is that life forms. We need geologists, we need biologists, right? We need chemists to look at basic chemical reactions happening in organisms. Moving further, especially when we come to intelligent life and then to intelligent civilizations that communicate, this is obviously then where social sciences are involved. The whole endeavor, the whole research in itself really requires a lot of philosophical thinking on what is life, what is even life, right? Like how can we define it? And in an age like today, where we are maybe able to soon develop something that is intelligent as us, but not maybe really live, but machine-based in artificial intelligence, would this also count here if AI at some point starts communicating over interstellar distances? So there are many questions involved here, and this is kind of where I want to end then this talk, and maybe maybe if we still have the time, come into a little bit of a discussion and or questions into into where this could go, but of course also questions going back to everything I have shown before. And with that, I say thank you so much, and my apologies that I went quite a bit over time, but I hope I was able to maybe already answer some doubts that otherwise would have turned up in questions.
Thank you so much. Not at all. In fact, I could have heard you a lot more, because I think I speak for my audience, our audience as well, that because we do not come from this field of study, and maybe just out of curiosity, only knowing that, oh, Pluto used to be a planet and now it's not. Outside of that, everything here that you said was very new, very exciting and fascinating also. I found those numbers very encouraging, from 0 to almost everywhere. So thank you so much. I'm not very sure if we'll have sciencey questions, but let's see if there are questions to things that you've said. I think you skipped a slide on probability of yeah, maybe we could come back to habitability a little later. So are there questions? Vedal and Gunjan have text written, long messages. I'm going to read them out. Vedal says, it was an amazing presentation. I was wondering that today, as you've shown us throughout your presentation, we truly have advanced technologies such as powerful telescopes and instruments, but can the discovery of exoplanets still be considered to a significant extent a matter of chance? That is one question. I'm surprised you could think, because my brain isn't thinking at all. I'm just too fascinated by what I've learned. Is this a matter of chance? And Gunjan, I mean, we would also love to know who you are. And if you could introduce yourselves, both Gunjan and Vedal. And Gunjan says, can there be exoplanet systems with multiple suns, central stars too, just like Star Wars? So those are the two questions. If there are any other questions, you may unmute yourself and ask those questions. Otherwise, we'll request Paul to start by at least answering these two.
Yeah. Should I maybe first answer these two and then?
Yes, please.
So that I don't forget. So I'll first answer Gunjan's question. I know that reference, and it's a very exciting one of that Star Wars system. So I'm not. So what I know for certain is that systems have been found where there's basically a planet orbiting a star, and then there's another star orbiting, that star and planet in the middle. Yeah. So these are things that have been found. What I'm not sure is whether there has been a system where you have two central stars basically, and then a planet orbiting or multiple planets orbiting around those two central stars. I don't think so. And this is, I mean, it might exist somewhere, but then the planet would have to be pretty far away from those two stars. And the reason is simply that basically a setup like this would lead to very complicated orbital dynamics. So stars are much heavier than the planets, and if you have two central stars orbiting each other, they would lead to a very changing gravitational field around them, right? And this would mean that a planet's orbit, if it's too close to those two stars, would not be very stable. And planets would probably be, you know, maybe they couldn't even form in the first place then. But if they could form, then maybe at some point they would be ejected out of the system or swallowed by the two stars. Both is not a very nice ending. But yeah, it's a theoretical possibility, definitely, if the planets have a little bit of a distance to those two stars. And looking at the first question, so is it still to a significant extent a matter of chance? So I would say to a certain extent, it's a matter of chance. And the reason is, so I've shown, for example, for the transit method, right, where the planet moves in front of the star, and we see that brightness dip. This obviously only works if the planet moves in front of the star. But there are many other possible constellations, and those other constellations are much more probable. That is, for example, that we look at the whole system face on. So we look at the star, and the planet orbits basically, you know, in the line or in the plane of the sky, right? And not in between us and the star. That's much more likely. So for one single system, it is basically always a matter of chance whether we find something. But usually nowadays, you know, we have large scale surveys that look at many, many different stars, either at the same time or in quick succession. And, you know, looking at the statistics we know today, these surveys usually can kind of predict fairly well how many planets they should be able to detect. So, you know, by and large, it's not really that much not that much a matter of chance, only for like individual systems.
Any other questions? If it's not a question, if you want to say something. Okay. Paul, if you're comfortable, I would want you to talk about that one slide that you missed as well.
Sure, I would love to. So it's the slide right here. So probing habitability. I had said earlier, I had kind of shown the habitable zone, which is the zone around a star where, you know, one is in the sweet spot between basically being too close to the star and too far away. So temperatures can be kind of comfortable on a planet. And I had said that, you know, but this is obviously not the only factor, but atmosphere of a planet, for example, is also important. We know from the atmosphere on Earth, right now we're running a big experiment here on Earth. What happens if we change, you know, the fraction of carbon dioxide by a little bit? And we notice a lot changes, right? It gets much warmer. It leads to huge changes in the climate. It leads to extreme weather phenomena and all of this. So this really shows how important atmosphere is and the exact kind of contribution or distribution of elements and how the atmosphere is made up. So we want to basically see, we want to understand those planets better. We don't just want to know the mass and the radius and how far away is it from the star, but we also want to understand, is it rocky or not, and what does it have an atmosphere, and what does the atmosphere look like? And this can be done with transmission spectroscopy, where we see kind of the picture down here. So again, if for the transit method, the planet moves exactly between the star and us during its orbit, then a little bit of the starlight will always go through the planet's atmosphere before it comes to us, right? As long as the planet has an atmosphere. And this means that if we again take a spectrum of that, we will not just see the stellar spectrum, but we will also see the imprint of the planet's atmosphere on this spectrum. And this is kind of shown in this picture on the lower left, where you have these two lines in the spectrum in the kind of yellow-orange region. And those are then those are absorption features of the atmosphere of the planet. And on the right-hand side, you see one recent example by the James Webb Space Telescope. So that's for the planet GJ9827d. This exoplanet names are never very nice. And so authors looked here at the data that was collected and kind of tried to model this with, very complex atmospheric models. And there's again, still a lot of uncertainty here, but here they could show with a very high certainty that there's H2O, so water in the atmosphere. So basically all of these bumps where it goes up, this means that more starlight is absorbed by the planet's atmosphere there because of water in the atmosphere. And for this exact planet, because we know it's probably roughly 300 degrees Celsius hot, it will be steam, and so a steam atmosphere. And this is exciting again, because it first of all shows us we can, at least for some planets, analyze the atmospheres of these planets, even though in this case, I think this system is 100 light years away. And we find water on other planets. And, as for the life we know, life on Earth, water is one of the most important molecules, right? So this is why this is exciting. And this is very up-to-date research that is going on, and JWST, the James Webb Space Telescope, looks at many other systems and planets, and similar kind of analysis are being done.
Thank you. Are there questions, concerns? All right. So what we've understood is that there is a possibility, and we have these fancy instruments which are looking out for other planets. And on a lighter note, Pluto's not alone. At least Pluto wasn't removed from the list of planets alone. There's another one right there. So Aries, if I'm not wrong. And yes, and I've taken extensive notes. 51 Pegasus is the other one. So we have a number of exoplanets in research in that direction. And some of the formulas also I found, in fact, I think for somebody who doesn't work in this area or hasn't read this literature, I learned a lot and I understood a lot. So thank you so much, Paul. I wish we had Paul-like teachers, which is me going back and saying we didn't have very good science teachers quite directly, but I wish we had teachers who would make some of these difficult conversations as easy as you did. So thank you so much for that. I would now request Pratham to formally thank a speaker and also our participants who could join us today. And to Pratham now.
With this, we come to the end of the session. We thank our speaker, Dr. Paul, for what was a fascinating, interesting, intriguing, but also extremely accessible session. Thank you so much for that. On behalf of the entire DARK team, I extend a heartfelt gratitude to you. We are also very thankful to all the audience members who today sat with us today and just listened to Paul and really ask very interesting questions. We hope to see you in future sessions of the Baithak as well. Thank you so much. That's all for today. Thank you so much.
Thank you.
Thank you. Thank you, everyone. And we'll probably host another Dark Baithak coming Saturday. And hopefully with Paul starting it for us, we'll probably bring in more people who could speak to us about science and educate us. And thank you so much, Paul, for doing this, taking out the time. I also know that you're probably not working in this area right away for some time. So I know you must have come back to it to give us this presentation, for which we are most grateful. Thank you so much.
I'm grateful for the opportunity. As you said, I'm not working in this area anymore, but it was fantastic to be able to come back for this opportunity. So thank you so much for that.
Thank you. Thank you so much. Have a good evening and night, everyone, and happy weekend.
Thank you. Goodbye, everyone.